Welcome, everyone. Today, we're going to explore the fascinating world of fuel cell technology, a cornerstone of sustainable energy solutions. A fuel cell system is far more than just the core reaction. It's an intricate integration of many components working in harmony to produce clean electricity. We'll delve into the polymer electrolyte membrane, or SPM, fuel cell, which is widely recognized for its efficiency and versatility. We'll cover everything from the basic chemical reactions to the critical balance of plant systems that ensure reliable operation, and finally, why these technologies are so crucial for our future. From transportation to stationary power, fuel cells offer high efficiency and zero tailpipe emissions, supporting a cleaner hydrogen economy. Let's start by looking at the core reaction where hydrogen and oxygen combine to create electricity, water, and heat. Let's focus now on a key area within the fuel cell, the cathode, often referred to as the positive terminal. This is where oxygen plays its vital role. Here, oxygen from the air enters the system, ready to react. Protons, which have traveled from the other side of the fuel cell, arrive, along with electrons that have completed their journey through an external circuit, generating electricity for us. These three components, oxygen, protons, and electrons, then combine at a catalyst layer. The result of this combination is the formation of water, which is the only byproduct, along with the release of heat. This completes the electrochemical cycle, marking the end of the energy conversion process within this side of the fuel cell. Continuing our journey into the heart of the fuel cell, we revisit the cathode side. This is where the crucial final steps of the electrochemical reaction take place. Think of it as the point where all the elements converge to complete the energy generation cycle. Oxygen, supplied from the air, meets up with the hydrogen protons and electrons that have been guided through the system. At the catalyst, these three essential components react to form water. This water is a clean output, and importantly, heat is also released during this process. This efficient combination not only provides a clean energy source, but also illustrates the elegance of how the fuel cell converts chemical energy directly into electrical energy, concluding its internal process. Central to the operation of a PEM fuel cell is the proton exchange membrane, or PEM, which acts as the electrolyte. This incredibly smart membrane has a very specific job: to permit only positively charged hydrogen ions, or protons, to pass through it. While allowing protons to travel freely, it acts as an impenetrable barrier to electrons and gases, effectively separating the fuel on one side from the oxidant on the other. This separation is crucial as it forces the electrons to take an external path, creating the electrical current we harness. Maintaining the membrane's hydration is key to its conductivity and overall performance. The PEM's integrity and selective permeability are absolutely critical for the fuel cell's efficiency, power output, and long-term reliability. The catalyst layer is where the magic truly happens inside a fuel cell, enabling the chemical reactions that generate electricity. This layer, typically made with platinum particles supported on carbon, is strategically placed on both sides of the membrane. Its primary function is to significantly speed up the electrochemical reactions of hydrogen and oxygen, making the energy conversion efficient enough for practical applications. Platinum is chosen for its excellent catalytic properties, but its cost and scarcity present a significant challenge. Researchers are constantly working to reduce the amount of platinum needed or to find alternative materials. This layer's effectiveness is paramount. It directly impacts the fuel cell's performance, durability, and ultimately, its commercial viability. The gas diffusion layer, or GDL, is a vital yet often overlooked component in a fuel cell. Positioned on either side of the catalyst layer, it performs several critical functions. Firstly, it facilitates the even distribution of reactant gases, hydrogen and oxygen, from the flow channels to the catalyst layer. Secondly, it serves as an electrical conductor, allowing electrons to move efficiently. Thirdly, it provides structural support to the delicate membrane electrode assembly. And finally, and perhaps most importantly, it manages the water produced by the reaction, ensuring it doesn't flood the catalyst layer while also preventing the membrane from drying out. A well-designed GDL is crucial for optimal gas transport, electrical conductivity, and thermal and water management, all of which are essential for fuel cell performance and longevity. Bipolar flow field plates are fundamental components within a fuel cell stack, performing multiple critical roles. Essentially, these plates create the pathways for gases to flow to and from the catalyst layers. On one side, they channel hydrogen, and on the other, oxygen. Their intricate designs ensure uniform distribution of these gases across the active area, maximizing reaction efficiency. Beyond gas distribution, these plates also serve to collect the electrical current generated by each cell, connecting them in series to build up voltage. They are also crucial for heat removal, preventing the stack from overheating and providing structural integrity to separate individual cells. Effective flow field design significantly influences the fuel cell's performance, power density, and overall durability. A single fuel cell typically produces a very small voltage, usually less than 1 volt. To achieve the practical power levels required for real-world applications, individual fuel cells are connected in series, much like batteries in a flashlight. This assembly of multiple cells is known as a fuel cell stack. Each cell contributes its voltage, and by stacking them, the overall voltage and power output are significantly scaled up. The stack is the powerhouse of the system, where the collective reactions generate substantial electricity. Designing and manufacturing robust, efficient stacks that can withstand operating conditions over thousands of hours is a key engineering challenge, ensuring that the cumulative power is reliably delivered. Current collectors play a vital, though often unseen role in the overall performance of a fuel cell stack. Their primary function is to efficiently gather the electrons generated at the anode and conduct them away from the cell through the external circuit and back to the cathode. Made from highly conductive materials, they minimize electrical resistance, ensuring that as much of the generated power as possible is delivered to the load. These components are strategically placed within the stack to ensure an uninterrupted flow of electricity from cell to cell and eventually out of the stack. Efficient current collection is essential for maximizing the power output and overall efficiency of the fuel cell system, ensuring the electricity reaches its intended destination. Within the complex structure of a fuel cell stack, seals and gaskets are absolutely critical for safe and efficient operation. Their primary role is to create gas-tight barriers, preventing the leakage of hydrogen and oxygen, while also ensuring that these gases are directed precisely through their intended flow channels. They must withstand the challenging operating environment within the fuel cell, including varying temperatures, pressures, and chemical conditions, often for thousands of hours. Preventing hydrogen crossover or oxygen leakage is not just about efficiency, it's a fundamental safety requirement. The durability and integrity of these sealing components are paramount to maintaining the stack's performance and ensuring the long-term reliability and safety of the entire fuel cell system. Maintaining optimal operating temperature is paramount for the performance and longevity of a fuel cell. And this is where the cooling system comes in. Fuel cell reactions generate heat as a byproduct. And if not effectively managed, this heat can degrade components, reduce efficiency, and even lead to system failure. The cooling system circulates a coolant, often a water glycol mixture, through channels in the fuel cell stack. This fluid absorbs excess heat and then dissipates it via a heat exchanger, much like a car radiator. An effective cooling system ensures the fuel cell operates within its ideal temperature range, maximizing its efficiency and significantly extending its operational lifespan. The proton exchange membrane, the heart of our fuel cell, requires precise hydration to function effectively. This is the crucial role of the humidification system. If the membrane dries out, its proton conductivity drops, severely impacting the fuel cell's performance and potentially damaging it. Conversely, too much humidity can lead to water flooding, hindering gas flow. The humidification system carefully adds moisture to the incoming reactant gases, particularly air, ensuring the membrane remains at its optimal hydration level throughout operation. Achieving this delicate balance across varying operating conditions is a significant engineering challenge, yet it is absolutely essential for sustained efficiency, durability, and reliable power output from the fuel cell. For a PEM fuel cell, the cathode requires a steady, precise supply of oxygen, typically sourced from ambient air. This is the task of the air compressor or blower. These components draw in ambient air, filter it, and then pressurize it before delivering it to the cathode side of the fuel cell stack. The amount of air, its pressure, and its flow rate must be meticulously controlled to match the fuel cell's power demand. An efficient air supply system is vital for maximizing power output, optimizing overall system efficiency, and ensuring the reactions proceed effectively without starving the cathode of oxygen. Selecting the right compressor or blower technology, balancing efficiency with noise and cost, is a key consideration in fuel cell system design. The hydrogen supply system is the lifeline of the fuel cell, responsible for safely and precisely delivering hydrogen to the stack. This system involves several critical steps: storing hydrogen, often at high pressures, then regulating that pressure down to the fuel cell's operating requirements. It also ensures the hydrogen is purified to remove any contaminants that could degrade the fuel cell. Finally, it controls the flow rate to match the electricity demand. This complex network includes tanks, valves, regulators, and sensors, all working together to ensure a continuous, clean, and safe supply. The integrity of this system, its safety, purity control, and leak prevention is paramount for both performance and the reliable operation of the entire fuel cell. Power electronics are the essential bridge between the fuel cell stack and the application it powers. The fuel cell produces direct current, or DC electricity, and power electronics are responsible for conditioning and managing this power. This can involve converting the voltage to meet specific requirements, or changing it from DC to alternating current, AC, for grid connection or various electrical devices. They also integrate the fuel cell with other components, such as batteries in a hybrid system, managing charge and discharge cycles. These intelligent systems ensure the electricity is delivered efficiently, safely, and in the correct format for its intended use, whether it's propelling a vehicle, powering a building, or charging a battery. At the very heart of a reliable fuel cell system lies its sophisticated control and safety system. This intelligent brain continuously monitors every critical parameter: temperature, pressure, flow rates, voltage, and current, across all components of the fuel cell. Based on these inputs, it dynamically adjusts operation to maintain peak efficiency and prevent any deviation from optimal conditions. More importantly, it acts as the guardian of the system, implementing safety protocols to detect and mitigate any potential hazards, such as leaks or overheating. It ensures that the system responds appropriately to both normal operating conditions and unexpected events, guaranteeing safe, stable, and highly efficient performance throughout the fuel cell's entire operational lifespan.